How many unwanted phone calls are you receiving each day? There was a time a couple of months ago when I was getting what felt like a lot more than usual. So naturally, I was thinking about this a lot, and I decided to turn it into a math exercise by modeling the number of phone calls that I was receiving each day. I'm going to model this as a Poisson distribution, and I will explain to you why I feel that this is the appropriate probability distribution to use. And then I'm going to be using a chi-square goodness of fit test, and I will make some comments about things that I had to do in my data collection to make it work, but I will not be fully explaining either the Poisson distribution or the goodness of fit test in this video, because I have two other videos already about those topics, which I'm going to link in the description. So in a sense, I am going to assume that you know what these things are. So in my video about the Poisson distribution, I mentioned that one of the easiest examples is the number of people that arrive at a train station in a given period of time. And of course, you could change the train station for Starbucks or for any other place that you want, but it's the number of people that arrive during a specified time. And I also mentioned what I think is the other very common example, which is the number of goals scored during a soccer match. For that example, I even wrote a whole IA about it in a video that is linked here about the Qatar World Cup. But the thing that both examples have in common, the train station and the game, is that you have a thing that is happening at random intervals of time, whether it be a person arriving at the Starbucks or a goal being scored. And you want to count how many of those are going to happen in a specified time duration, but the intervals between the occurrences are random. So that is why the phone call example fits in this description as well. I am receiving phone calls at random times, sometimes two very close together and sometimes hours apart, but I am receiving several phone calls during the period of a day, which is the number that I'm interested in modeling, the number of phone calls per day. So the first thing that I did, obviously, was to go to my cell phone and just start counting the number of calls that I had received each day. Obviously, I didn't pick up any of those phone calls, but they're still registered on the phone. And I put all that information into a spreadsheet. Now, I am not going to be writing out this example today completely as an IA, but if you are an IB student, of course, you can think of this as an example of an idea that could be used for your IA. I am just not going to be writing it down and talking much about rubrics today because I have done that already in a bunch of other videos. There's a whole playlist here if you want to go see me making comments about the rubrics of the IA. So today I'm just going to be going through the exercise. But one question that I get a lot from students when they are working on their IA is, how many data points do I have? Like in this case, how many days should you go look at your phone and see how many phone calls you got in each day? And like, I don't know, it's pretty random. I did that until I got bored. Generally, the more data you have, the better. So when I put it in the spreadsheet, the first thing that stood out very clearly to me was that Saturdays and Sundays were completely different. Maybe that makes sense in the real world for some reason. I don't know. But as for the numbers, what that means to me is that I really do want to take those days out of my spreadsheet. I want to change my aim a little bit to model the number of phone calls that I get each weekday by a Poisson distribution. So if I was writing an IA, I would make this comment, which shows a little bit of reflection about the data set. So anyway, after removing Saturdays and Sundays from the data set, the next thing that I did was to get the spreadsheet to give me the average number of calls for those days that I had written down. And to my big surprise, it was a perfect round 3 calls per day as an average. That was unusual to get such a round number. But of course, I was looking for the average because that is the parameter of the Poisson distribution that I'm going to want to use. It's a Poisson distribution with average 3. Say that the number of phone calls in a day is distributed like this Poisson variable. So what is the probability that the number of phone calls that comes out today is 2? Or what is the probability that the number of calls today is 5? That is the probabilities that we're going to be calculating. And then we're going to see how many days did have 2 phone calls, how many days did have 5 phone calls, and so on. So the next thing that I did after that, and this goes a lot to how the chi-square goodness of fit test works, If you don't know about it, I really recommend the other video, which is that having this number, having this parameter, I now want to calculate in how many days I expected to have each number of calls. So my total data set was something like, I don't know, 30 days or something like that. So out of those 30 days, for a Poisson distribution of mean 3, how many of those days were expected to have exactly 3 phone calls? In how many days would I expect to see 2 phone calls, or 1, or 0, or 4, 5, and so on? Those are numbers that you have to calculate in order to do the chi-square goodness of fit test, because then you're going to compare these expected values with the actual values from the data set. How many days did I get 3 phone calls? But there is a thing, there is a detail about the goodness of fit test that says that none of those numbers, those expected numbers, can be less than 5. And I've talked about this before in other videos. It's not like 5 is a magic number, but it's somewhere around 5. So maybe if I had a 4.9, I would still be okay with it, or something like that. But with the numbers that I had here, with around 30 days and the average 3, then the expected number of days with 0 calls was a lot smaller than that. Again, at this point, if you were writing an IA, you have to argue a little bit about your choices and what you're going to do now, because one thing that is very common to do in goodness of fit test when you have these very small categories is to put them together. So I could put 0 and 1 together and say, what is the probability of getting less than 2 phone calls? Would be a category, which includes both the 0 and the 1 phone calls per day. But the thing is that my choice in this moment is that I didn't want to do that, because I feel subjectively that 0 and 1 is a lot more different than, say, 1 and 2, because 0 is like no phone calls at all. 1 and 2 are both like very few phone calls. You know, it's a bigger difference that maybe I don't want to lump together. So instead of that, my choice was to just increase the number of days. So if we don't change the parameter of the Poisson distribution, that's not going to change the probability of getting 0 phone calls that day. But if we do increase the number of days that we are looking at, the probability didn't change, but the expected number did change, because you're going to have to multiply that probability by the total number of days. And that was my plan, to just keep looking at more and more days until I got that category to reach the number 5. So at some point I ran into the problem that my phone's history didn't go far back in time as much as I wanted it to. There was a limit to how much data I could collect. But it all worked out, because those new data points that I was collecting afterwards had smaller numbers, so it ended up lowering the average as well. And I was able to get my categories less than 5. I did combine the categories for a large number of phone calls, right? But that is fine. By the same argument where I feel like 0 and 1 are very different, I don't think 7 and 8 are different at all. That's just a very big number of phone calls, so it's okay for me to have those categories put together. All right, so now that I've finished doing all of that, the only thing that still remains to be done is to actually run the chi-square goodness of fit test. So I went into my TI-84 and I typed the two lists here. In L1, I am putting the observed values, and L2, the expected values. So that 17 is, for example, the number of days in which I got 0 phone calls, and then the 10 is like the number of days in which I got just 1 phone call, and so on. And on the other list, 5.844, for example, is the expected number of days in which I would get 0 phone calls that day, if the thing was actually modeled by a Poisson distribution with average 2.42, something like that, was what it ended up being when I collected 66 days instead of 36. And you can already kind of see that these two lists look a little bit different from each other, right? But let's see what happens. So here I'm telling the calculator where the observed values are, the expected values, and degrees of freedom right now it's 4, because I have 6 categories for 0, 1, 2, 3, 4, and then 5 or more days, which was the category that I combined in order for the expected number to not be very small. So I have the 6 categories. I always have to subtract one of the categories due to the fact that I'm making sure that all of the expected values add up to 66. And I lose another degree of freedom due to the fact that I am forcing the average to be 2.42, which was the average that I got from my observed values. Anyway, when I get the TI-84 to calculate that, my result for a p-value is 5.44 times 10 to the negative 7, which is extremely small. And I realized that I didn't even talk to you about the significance level that I was going to use, which is usually 0.05. But with 5 times 10 to the negative 7, it doesn't even matter to talk about that. This value is just extremely small, which means that it is extremely unlikely to get these values if the thing was modeled by a Poisson distribution like I'm trying to do. We had already noticed in the table that the values were very different, and here is the same information presented again graphically. So the red is the observed values and the blue are the predicted values. You can see that the blue values are much more well behaved. They start very small in 0 calls per day, then they go up until 2 calls per day because the average is 2 point something, and then they go down again. And the red values, which are the observed values, are more all over the place. I have 17 days with 0 phone calls. That is way too much. And this is a point where if this was a student writing an IA, sometimes people tend to panic. And I want to help you calm down. Because a student will look at this and say, oh no, my IA did not work. So I have to throw everything out and start over again with a brand new idea. No, that's not the case at all. There is no such thing as an IA not working. You asked the question, right? Can this be modeled by a Poisson distribution? And if the answer to the question turns out to be no, who cares? You still did the math. You still showed that you understand the concepts. So it is still a good IA. If anything, when things don't turn out the way you expected them to, it opens up more opportunities for reflection. And reflection is in the rubric. You will get points for reflecting upon this. This whole thing that I was just saying about the blue values being more well behaved than the red values is already a little bit of reflection. And I would also point out that if we look at the data in a different visualization, this is the horizontal axis is time. So I have all the 66 different days here in chronological order with their respective number of calls. And what we can kind of see here is that my original impression was kind of right. When I started thinking about this, I got the feeling that I was getting more calls than usual. And if we look at this graph, there is a whole chunk of graph in the middle that is way higher than the beginning and the end. So that was like a month ago already when I stopped collecting the data. But since then, I haven't been getting that many calls. So I can assume that I am back to this level of zeros, ones, and twos. But I did go through a period of a lot of fours, fives, and sixes. So that is why when I look at the whole thing together and try to model it as a Poisson with one average, which is 2.4, it doesn't quite work because there are different time periods within that data set. And that is a perfectly fine conclusion to an IA.